Alright, so in this section 2.3 we talk about using some actual limit laws, concrete ways in which to calculate limits quickly. Alright, so if you got some function f and its limit exists, and you got some function g and its limit exists, then all of these things can be true now. So the limit of f plus g is just the limit of f plus the limit of g. The limit of f subtract g is the limit of f subtract the limit of g. The limit of a constant times f is the same thing as constant times the limit of f. And again, in all of these problems, we would at this point already know what the limit of f and g are. Now, the limit of f times g equals the limit of f times the limit of g, and same thing for division. Also, you got to avoid g equaling 0. Alright, so here's a couple of quick ways to state all those different laws. Let's go on to example 1. Example 1 gives you the limit of f plus 5 times g. Well, here's your f, this guy here, curly one here, and g is the broken line one there. Alright, so the limit of f plus 5g is the limit of f plus the limit of 5g. And now you can bring that 5 out front using limit law 3. And so you get limit of f plus 5 times the limit of g. And we can see what the limit of f and g are at negative 2 of 1 and minus 1. So in place of f you put a 1, in place of g you put a minus 1, calculate it out, you get minus 4. Now this one, the limit of f times g, well, you can't calculate this one the way it is, because if you look at the limit at 1, f exists and is defined at 2. G does not exist. If you come at it from the two different directions, you get two different values. But if you want to, you can look at the limit laws for coming at it from the left and right. Coming at it from the left, you can say the limit of x as it approaches 1 from the left of fg, f times g, equals the limit as x approaches 1 from the left of f, times the limit as x approaches 1 from the left of g, which we now know was 2 and minus 2, which gives you 4. If you do it from the right, you get these two guys, and it gives you these other two values. And so you see you get a different answer for the left and right-handed limits. So because they're not equal, the limit does not exist. But again, you could have just said that up here just by this as well. Part C, what's the limit of f over g? Well, that's the limit of f over the limit of g. But the problem is the limit of g is 0, so we can't use rule 5 about quotients, and we have to say that the limit does not exist. Okay, so here's some more laws. The limit of f raised to the n is the limit of f all raised to the n. The limit of the nth root of f is the nth root of the limit of f. The limit of c equals c. The limit of x equals a. Notice as you're approaching a. The limit of x to the n equals a to the n as x goes to a. The limit of the nth root of x equals the nth root of a as x approaches a. Alright, so the first one, you break these up into 3 separate limits. You bring the 3 and the 2 out front, and now you're ready to take the limit of each one. And I believe they give you a picture that I didn't include here, but whatever. Alright, so the limit as x approaches negative 2 of this one is the limit of the top over the limit of the bottom. And then you got to take the limit of each one of these terms, and you want to bring the constants out front if you can. And then when you finally start plugging in numbers using direct substitution, you end up with negative 1 over 11. Now in example 2a, we determined the limit as x approaches 5 of f of x equals 39 for this function. Notice that f of 5 equals 39. In other words, we would have gotten the correct result simply by substituting 5 for x. Similarly, direct substitution provides the correct answer in part B. So the functions in example 2 are polynomial and rational function respectively, and similar use of limit laws proves that direct substitution always works for such functions. So, if f is a polynomial or a rational function, and a is in the domain, then as x approaches, limit as x approaches a of f of x is just f of a, direct substitution. Alright, functions that have direct substitution property are called continuous at a, and we'll talk more about that in 2.5. However, not all limits can be evaluated initially by direct substitution. Look at the following example. This guy here. We cannot use direct substitution property, or DSP, because 1 is not in the domain of f. We can't use the quotient laws because the limit of the denominator is 0. So what do? Well, let's factor it first. Note that x does not equal 1, so x minus 1 does not equal 0. So there's no division by 0 if you're talking about the limit, because we don't care what happens at 1. Alright, so if you look at this guy and you factor, you end up with x plus 1, and now you can do direct substitution and just get 1 plus 1 is 2. So let's say we call the original function f, and we call this new reduced function g. We can say that f equals g except when x equals 1. But the computing of the limit does not consider what happens when x equals 1, so we can do that. So the limit of this fraction equals the limit of this polynomial, which equals 2 by direct substitution. And you can see as you approach from the left and the right, you approach a y value of 2. Notice it is not defined at x equals 1. Now what if you take the exact same function but you define it at x equals 1 to be something different than 2? Well, g in example 4 is the same as f in example 3, except f of 1 is undefined and g of 1 is defined and equals pi. But they both have the same limit. They both approach the same y value of 2. Alright, so now let's look at 5. The limit of as h goes to 0 of this guy here. Well, you can't do direct substitution or quotient laws because you're dividing by 0. But what happens if you multiply this guy out, cancel your 9s, divide each term by h, and you get this? Now you can substitute in 0 for h. Direct substitution at that point. Alright, this guy is a problem because you're dividing by 0 and you can't do the quotient laws. But let's try and rationalize that numerator. So let's multiply this guy by its conjugate. Remember, a conjugate is simply changing the middle sign. The terms themselves don't change, but the sign does. Now when you multiply anything times its conjugate, you get the first guy squared minus the second guy squared. Right? Now if you've already printed out your notes for 2.3, you should add a t squared there and add a t squared there. I didn't seem to write that down initially. I didn't catch that. Alright, so when you multiply that out, you get t squared plus 9 without the square root, and you get 3 times 3 is 9. The bottom is kind of messy, but we don't care. I should probably put parentheses around that. Okay, and so your 9's go away, and you get t squared on the top, but now your t squared is going to cancel with the t squared on the bottom, and you just get 1 on the top, and you get this guy on the bottom. Now you can do direct substitution. Okay, the limit of this quotient equals the 1 over the square root of the limit of what's inside. Alright, and so you get, by direct substitution, you get 6. Now they talk about using one-sided limits. And they say a limit exists and is equals L if and only if the limit from the left and the limit from the right both equal L as well. Alright, so example 7. Show the limit as x approaches 0 of absolute value of x equals 0. Well, the absolute value of x equals x when x is positive or 0. And the absolute value of x equals negative x when x is less than 0. So if we look at it from the right, greater than 0, we're looking at this guy here, so we can substitute in what that is. And we know as we approach 0, that's going to equal 0. Now what about if we come at it from the left? Now we're looking at this guy here, so we replace the absolute value with negative x. And when we plug that in, we also get 0. Therefore, the limit equals 0. Prove that this limit does not exist. Well, if you graph it, you'll see clearly that it does not. But if you don't, come at it from the right, and remember the absolute value of x for positive values is just x, which is x over x is 1. Limit of 1 is 1. Coming at it from the left, we get absolute value of x over x equals negative x over x, and negative x over x is just negative 1, and the limit of negative 1 is negative 1. Since the left and right-hand limits are different, the limit does not exist. Example 9. This guy, it looks like this, very weird function. Okay, and if you take it from the right, you're looking at this guy here, and we can do direct substitution and we get 0. If you take it from the left, we're using this guy here, and we can use direct substitution and we get 0. Since the left and right hand limits are equal, the limit does exist and is equal to 0. Now the final idea that is talked about in this section is the squeeze theorem. Squeeze theorem says if you got some function g and you can't figure out what the limit is, if you can find another function f that is always less than or equal to g, find another function h that is always greater than or equal to g, then if you take the limit of each of those and you get the same answer, then g also has to have that same answer. Alright, so for this one here, x squared sine 1 over x, you start out with the second part here. You write out sine 1 over x. We know it varies between -1 and 1. And if we multiply everything by x squared, which we can do, we get this here. Now, here's your f, here's your g, here's your h. If you can get the limit of this guy and the limit of that guy that hopefully equal the same value, then you'll know that the limit of g is also that same value. Well, the limit of f is just the limit as x approaches 0 of negative x squared, which is negative 0 squared, or 0. The limit of h is as x goes to 0, is just 0 squared, which is 0. So now since f and h are less than and greater than respectively or equal to g, and they both equal 0, then the limit of g of x has to equal 0 as well.